Okay, we are in the 10 to 100 kilogram range still. You can see that these numbers don't always make sense, even though we are binning them into carbon footprint CO2 equivalents. So next up on our list is a quart of gasoline, which has 3.15 kilograms CO2 equivalent. What does it mean? Obviously, if you put it in a car, or you burn it on the floor or so on, you have different footprints, because if you take gasoline and just pour it on the ground and burn it, that's the carbon you will get. But when you put it in a car and you drive around, there are other impacts involved, as well as the carbon footprint of producing and transporting the gasoline, etc., also have to be considered. In the UK, we get through about 50 billion liters of gas and diesel per year. That's something like 4 bathfuls, right up to the brim, for every man, woman, and child in the land. Okay, so obviously we are an energy intensive species, and the question is, how do we decarbonize? Remember, we talked about carbon fractal. So if you look at the footprint of gasoline, it's just more than the CO2 that comes off the fuel, right? So you have burning the gasoline, which is about 75% of it, so almost 3/4 is from the end use. But extraction and shipping are adding 15% to the total. Direct emissions from the refineries themselves, about 9%. Electricity used by the refineries adding about 1%. And other factors, like including delivery to the pump, is about 1%. And then we have, of course, other things to worry about, like how efficient is your car, and whether it's got properly inflated tires, and whether you're a good driver, a bad driver, speeding at above the speed limit, and so on. So there is no clear boundary between the footprint of the gasoline itself and where it ends up being used and how it ends up being used. And that brings us to the point about diesel. Diesel is worse for climate than petrol. So if just from an engineering perspective, diesel is much more efficient in converting its energy into motion, which is what you're trying to do in an engine, and petrol is much less efficient, but diesel produces much more of a carbon footprint, especially particulate matter, which are really bad for health, which we are not looking at here, right? Life cycle of CO2 emissions from diesel and petrol cars. Total emissions per car in its lifetime, 42.65 tons of CO2. Again, very average kind of number across many per cars. Fuel blend with biodiesel would add 2.6 tons of CO2. Vehicle production adds 5.25 tons of CO2, and well-to-wheel fuel emissions, including refining, end up giving you 34.8 tons of CO2 to get this total number here. Okay, this is for diesel. If you now look at total emissions per car in its lifetime from a petrol car, so here we are assuming a mileage of 182,000 kilometers of lifetime. Fuel is B7 blend, 95% diesel and 5% biodiesel, which is another issue we have to worry about. So fuel blend with biofuel, it adds 0.8 tons of CO2. Vehicle production is adding 5, similar to here, but a little bit smaller. Wheel to wheel, did I say wheel to wheel? Well to wheel emissions, including refining, is 33.2, so it's lower than a diesel car, for a total of 39 tons of CO2 during a lifetime, with a mileage of 175,000 kilometers, and it's a E95 blend with 95% petrol and 5% ethanol. Ethanol has a whole lot of other separate issues in terms of land use, water use, emissions, etc. But coming back to biodiesel, it does have some advantages. So this is from the EPA site. I think I didn't put the site here, sorry. Feedstock inputs to US biodiesel production in 2019, total of 12.75 billion pounds. So soybean oil was 57%, animal fats, canola oil, recycled feedstocks, and corn oil made up the rest of it. And when you look at these, obviously you have to worry about competition with food markets, food prices, how it affects people who may not even be driving and are just trying to buy grains for food, for example. Okay, so there are those sorts of issues that are much more complicated when it comes to biodiesel, biofuel. And if you look at IPCC, it pretty much is convinced that bioenergy and carbon capture and sequestration are going to be necessary to meet our goals, global warming target goals, like 2 degrees C with a 66% probability. Forget about 1.5 degrees C, I'm not even going to worry about it. Okay, so there are other complications than just worrying about carbon footprint, but the focus here is only carbon footprint. Okay, so let's move on to rice, which also gets blamed a lot in the greenhouse warming context. 1 kilogram of rice has 2.5 kilograms of CO2 equivalent if it is efficiently produced. Everybody has heard of how the flood irrigation of rice produces lots of methane, and also agricultural practices produce N2O. So rice, which feeds billions of people, now is also considered hyperglycemic and not good for consumption of carbs and diabetes type 2 and so on and so forth. But it's not going to be easy changing people's dietary habits anyways, right? I love my rice. 4 kilograms of CO2 equivalent average is what you get for all types of rices combined and how they are grown. It jumps to 6.1 kilogram of CO2 equivalent if the cultivation is inefficient with excessive use of nitrogen fertilizer. A typical kilo of rice causes more emissions than burning a quart of diesel. Okay, so these kind of comparisons are not always completely end-to-end, but nonetheless, in general, you would say rice has, among foods, among grains, has a high impact on the environment through emissions. What does it do? The carbon footprint of 1 kilogram of rice in kilogram CO2 equivalent, if it is efficient production, it is under 3 kilograms, which includes methane from the paddies, fertilizer use, and transportation and processing and other agricultural emissions. We argued before that transporting food via airplanes is probably one of the worst things to do. But rice does get transported to across boundaries, international trade. Hopefully it's all being done by ships. Okay, inefficient production jumps the fertilizer use quite a bit here, and increased fertilizer use is going to reduce the methane a little bit from the paddy fields. Okay, slight bit, but it more than makes up for it in terms of fertilizer use and N2O production and other carbon footprints, not even worrying about downstream impacts on water quality and so on. Obviously, much thought is being given to improving rice cultivation methods, sustained intensified rice cultivation and so on. Use methods where seedlings are grown separately for a few weeks and then transplanted into the field, which reduces the flood irrigation, reduces emissions, and even argued to increase yields and so on and so forth. So in the context of total methane emissions by source for 2010, very hard to track methane across the globe, and right now you may be reading about satellites detecting massive amounts of methane emissions coming from Russia, which is pretty bad news. So this chart is created by Anna Maria Irriti. So this is the website where you can find it. So here is enteric fermentation livestock, which is a significant contributor. Rice cultivation is adding 10%. and then you have others like other agricultural sources, wastewater, oil and gas. Landfills are always bad news for methane. You have coal mining, which is a significant methane producer, agricultural manure here, and stationary and mobile sources like from vehicles and power plants and other things adding to it. Okay, just to touch on the N2O problem as well, if we look at methane and N2O emissions from rice cultivation, projected global emissions in 2030, global non-CO2 greenhouse gas emissions, the rice cultivation sector baseline emissions are estimated at 565 million tons of CO2 equivalent in 2010, which is what we looked at before. In 2030, emissions from this source are projected to be 756 million tons, or a 6% of total non-CO2 emissions. Again, looking here, energy, waste, agriculture, and rice. Okay, so where are the big sources? Emissions from top 5 emitting countries and rest of the world. So here you have 165 million tons, China adding 86, the rest of them here 162, 77, and 92. So you have India, Bangladesh, Indonesia, China, Vietnam, and rest of the world. Lots of rice gets consumed here, of course, and Japan, which consumes enormous amounts of rice as well, has to be careful how it uses the little bit of land it has. So they love their rice, they love their beef, but often depend on imports from other countries where transportation costs can obviously add up. Looking now at methane and N2O emissions from rice cultivations, emissions reduction potential in 2030. Assuming full implementation of current technology, emissions in the rice cultivation sector could be reduced by up to 200 million tons of CO2 equivalent in 2030. This accounts for 4% of the 4,615 million tons of CO2 equivalent in global reduction potential for non-CO2 gases in 2030. I have a chopper flying by here which is going to add some sound and pollution to my podcast, but nonetheless, here is rice and agriculture is all the green together. These are the potential for reducing greenhouse gases. So landfills have a huge potential. Refrigeration and air conditioning have to go to reducing their emissions, methane and N2O, because with warming and with developing economies, number of refrigerators and air conditioners are going up exponentially, which is not good news. Of course, oil and natural gas systems and other energy systems together have a huge potential, as well as waste. Okay, so that is now combining slowly. I'm just merging bigger issues with just the carbon footprint, but it's better if you know the carbon footprint of your rice and your gasoline, for example, along with all the associated issues that go with it, so that you are still aware of what you can contribute, how much you can actually control versus what the system is going to trap you into, in the sense of that carbon fractal that we talked about before. Okay.